All right, first thing I want to go over is making sure that, just reminding you that I think most of you have signed up, but for those of you who haven't, if you guys can take care of the AP exam registration, it's available. The directions are under the general tab or general channel. I also just want to let you know that I included the AP Classroom link at the top of the your general Teams page. So, so for future reference, if I ever ask you to do anything, any assignments through AP Classroom, you can just click on that link, and that'll take you to our class page within AP Classroom. Right, so if you guys can take care of that today, for those of you who haven't done so, that'll be great. I'm going to go to the class website just to highlight a couple of things about this week. So this is where you've been going to find your notes. So today we're going over 1.4b. We're doing intermediate value theorem. I'm going to start including some review worksheets or practice worksheets, because we just don't do a whole lot of practice problems in class, shortened period, and me just trying to get through the lesson. So this is not going to be required, but for those of you who just feel like you want some extra practice beyond what we, because we're doing kind of minimal practice problems in class because we just don't have time. But this is not required. But if you were to look in here, you're going to see some continuity problems, some IVT problems, some problems that we're going to cover on Friday for limits approaching infinity. You may see some duplicates. I may have pulled some problems from here. But the first part is our blank student handouts, and the second half is the key with the worked out solutions. So just for additional resources for you all. If there's any questions here, or there's any questions in general, and you're stuck on the problem, feel free to message me through Remind. You can take a photo of the problem that you're stuck on, or you can also join mornings at 7:45 in the Calculus AB help session page or Teams page. You guys should all be on that. I think I added all my students there, so you can always join 7:45 in the mornings if you want me to go over any additional problems with you. Okay. Tomorrow, you guys will be doing iReady pre-assessment diagnostic test. And this is going to be across the board. All the students have to take it who are taking math this year. So here are the instructions. I have the instructions here, but if you click on this link, the teacher put this together where the link includes not only verbal instructions, but also screenshots of what you should be seeing along the way. So you may want to test this out sometime today just to make sure that you're able to get that iReady icon and that you can access it and you're able to see math diagnostic. Okay. And so tomorrow what's going to happen is I want you guys to come into the Teams class just for the first few minutes. So just come in, check in, have the system acknowledge you, and so that so I can take attendance. I just want to be able to take attendance, but as soon as you come in, you can just leave and then go and take your iReady test. So I will send out a reminder this afternoon to remind you to check in first at the beginning of class before you take your iReady test. So also I want you guys to put your best effort into it. If you just end up, just choosing random answers and just trying to get out of it, you may be asked to take it again. So, just try your best, and so that all the teachers will kind of know or have an idea if there are any potential gaps that we need to address within our class for our students. So another student was asking from a previous class whether they can take it earlier or not. Do they have to wait until this class period to take it? And I don't know the answer to that. So once I find out, I will include that in the remind text I send this afternoon. Okay. I think the idea is that they want students to take it in the class period that they have math, but I don't know about if there's an option to take it outside of class. And if you are not able to finish it in time, you can always come back to it later and then submit it. So you can always leave the test and then come back to it and finish it later. So if you feel like you're rushed for time or something happens, you can always exit and then come back in and then finish it and then submit it. All right, any questions about tomorrow? I will stay on the Teams channel in class. So after you guys leave, I'll still be on. So, if there's anything that happens and something goes wrong or you need assistance, you can always log back in and I can try to help. Okay, no questions for tomorrow? Okay, let's do notes for today. Intermediate value theorem. I'm going to skip the warm-up problem. This is a good problem to do, but this goes back to continuity conditions with piecewise functions, which I think is good for us to do, but I was struggling to get through the lesson just going through these two examples in the allotted class period. So maybe I'll save this for Friday. Okay. All right, let's start off with continuity on the closed interval. So if a function is continuous on an open interval, so here's my open interval from A to B. And we want to know whether this open interval is going to connect to the endpoints. We can test using this formal language here. So what this is saying is the limit as x approaches a from the right side of a. See that plus sign? That means we're starting at a point to the right of a. And then we're going to follow the path towards a. So if the path that this leads us to is the same as the endpoint, then we know that this open interval, this segment, is going to connect to this endpoint. Likewise, on the other side, limit as x approaches b from the left side of b, so one-sided limit. See that negative sign? That means we're starting to the left of b, and then we're moving towards b. So we follow the arrow towards b. This is leading us towards a y value, which also matches with the endpoint. And so now we can have a formal language that guarantees that the function is not only continuous on the open interval, it is also continuous on the closed interval. So it's going to connect from endpoint to endpoint. Okay, so the big topic for today is IVT, intermediate value theorem. So when I think of the word intermediate, it kind of reminds me of the word middle, right? It's kind of, if you think about an intermediate step, it's kind of like a step in the middle. So if you think about that word middle, I think that will kind of help us visualize what we're trying to achieve. And we're basically trying to show that a middle value exists. But if we want to guarantee a middle value, we need to have a low and a high value, right? In order to achieve that middle, it has to fall between 2 points. So we're trying to find that guarantee, seeing if that middle value actually falls between a lower and upper value. Let me read the formal definition first, and then I'll go through further description, and then we'll look at some examples. Okay, if a function is continuous on the closed interval, let me just go ahead and highlight that, because this is an important piece that we're going to have to be able to state and test for pretty much every theorem that we come across from now until the end of the course. So this is a important condition that we need to establish first. We'll talk a little bit more about how to establish that, but so let's say our function is continuous, okay, no breaks, no holes, no asymptotes between our endpoints. And k is any number between f of a and f of b, so k is number between f of a and f of b. Then there's at least one number c on the x interval from a to b where f of c is equal to k. So in other words, what this is saying is, if a function is continuous, no breaks in the graph, then this graph is going to touch every y value between the two endpoints, at least once. So if we follow this example here, let's say one endpoint starts at the y value of 5, and then the other endpoint ends at a y value of 1. Every y value between 1 and 5, the graph is going to touch at least once, right? We know that this graph is going to hit 4.9, 4.6, 3.2, 2, 1.1, right? Every y value you can think of between 5 and 1, this graph is going to touch. So that's what intermediate value theorem is guaranteeing. But in a more specific way, we're going to know what target we're trying to reach. Let's say we're trying to guarantee a y value of 3. So what we're going to do is we're going to find the endpoints, and we want our endpoints to be above and below so that we can have that target to be in between, to be an intermediate, to be a middle value. If we can show that our target is a middle value, then we can guarantee that it's going to have to hit somewhere between, even without looking at the graph, right? So we're trying to make some guarantees about the graph without looking at the graph. So what we do is, okay, let's establish it's continuous. Let's establish our endpoints are above and below, and then from there, we know that we can guarantee this middle value. Okay, any questions about the definition or the diagram before we look at example 1? Okay, so here's example 1. Use intermediate value theorem to show that there is a 0 in the interval from 0 to 1 for the function x cubed plus 2x minus 1. Okay. So this is the y value we're trying to guarantee. Okay, we're trying to guarantee, we want this to be a middle y value between our two endpoints. Can we guarantee And can we show that this is going to be a middle value, middle y value of 0? And the way that we're going to compare and determine if that is a middle y value is we're going to use these intervals, use these endpoints. But something to be aware of is that these are x values of the endpoints. And it's important that we are clear on that, because we never want to compare these numbers with this number, right? We never are going to ask, wait, does 0 fall between 0 and 1? Because they're not at this, we're not talking about, we got to compare y values with y values. So make sure that we don't try to compare x values with y values, because then we're not matching the same things. So we need to do some work to find the y values so that we can actually test to see if those endpoints have a y value above and below 0. Okay, so that's our end goal. Okay, that's our end goal. But before we jump to that, we have to first establish our condition. So our condition is continuous on the closed interval. The nice thing about this problem is that this is a polynomial. The nice thing about polynomial is that it's continuous everywhere. So that saves us time. We don't have to do additional checks. We don't have to worry about, wait, is there a vertical asymptote, or is there a hole that's going to affect my my statement? So whenever you see a polynomial, meaning that you don't see any variables in the denominator, you know you're safe. You can just we can just make this statement and not have to worry about anything, any issues with continuity. So it's important that we write not just continuous, but continuous on the closed interval, because we only care about what's happening between the interval. True, it is continuous everywhere, but we want to establish that it's the endpoints that we care about. Okay, so now that we have our condition out of the way, we have to look to see if 0 is going to fall between our y values, our endpoint y values. So to do that, we're going to have to find our y values from 0 and 1, and we're going to plug in and actually find the y values at those endpoints. Okay, so we'll plug 0 into the function. Okay, and we get -1, and -1 is lower than 0, so we have a number that's below 0. And we have one endpoint below 0, which means that we're going to need the other endpoint to be above, right? We need 0 to fall between our endpoints. We want this to be the middle value, the middle y value. So let's move on to our other endpoints. We'll plug 1 in for x. One plus 2 is 3. 3 minus 1 is 2. So I think we're good, right? 0 falls nicely between -1 and 2. If we start at -1 and we end up at 2, we're going to have to touch 0 somewhere between. So 0 is an intermediate value between -1 and 2. Those are the numbers we're comparing, and that is what we're using to determine whether we can prove that there's a 0 through intermediate value theorem. Now, if both of these numbers were above or both are below, then we're not able to show this as an intermediate value, right? If this was -3 and this was -4, okay, maybe the graph does dip above and come back down and actually hit 0. But without looking at the graph, we're restricted, right? We're relying on this information to make that conclusion. So if the endpoints are not providing what we need, this IVT is not a good way to guarantee that value. If that's the case, we would say IVT doesn't apply because 0 doesn't fall between our endpoints. Okay? But in this case, it does. So this is how we are going to make our conclusion here. We'll say by IVT, and we're actually going to state the fact that we are comparing that 0 with the endpoints, and that 0 falls between our endpoints. So the way we say it is, since our endpoint f of 0 is -1, and this value is lower than 0, and 0 is lower than the other endpoint, which is f of 1 equals 2, then we can guarantee that 0 is going to show up sometime. So we can guarantee that f of c is equal to 0. And c is just a, you're going to see, c is just a specific x value solution we're looking for. Which in this case, we're not going to find. It's not asking for us to find the c value, but we just know that there's an ordered pair where there's going to be a y value of 0. And that this location is going to be in the interval from 0 to 1. So if we were to locate the ordered pair, that x value is going to have to be between 0 and 1, because that's our x value interval. Now, you don't have to graph this, but I just want to kind of show you what the graph looks like. So, if you're having trouble visualizing, where the x's are, where the y's are, and why we're comparing these numbers, this is what we're working with here. So this is the graph of x cubed plus 2x minus 1. We're looking for a y value of 0, right? We're trying to guarantee, can we guarantee a y value of 0? And we have to rely on the endpoints. So we're plugging in our x values into the function, and we're getting -1 and 2. And that's how we know, because -1 and 2 are on either ends of 0, we know the graph is going to cross through a y value of 0 somewhere between my endpoints. And we can say that we don't know what the c value is. We don't know what the exact order pair is, but we do know that an order pair is going to exist where that c value is going to fall between 0 and 1. So that c value is going to have to be, maybe 0.5 or 0.3 or 0.1 or 0.9. We don't know it yet, and we don't have to find it for this problem, but we do know that there must be a point, must be an order pair where that x value is going to fall between 0 and 1. Okay, any questions there? Okay. All right, let's try the example on the back. Okay, example 2. Verify that IVT applies for our function on the interval from 5/2 to 4 for f of c equals 6. But we're going to go one step further. We're going to find the c value. We're actually going to find the ordered pair where that specific point is on the graph. So let's try to organize this information here. We know that this is our goal here. We're trying to, our goal is to guarantee without looking at the graph, can we guarantee that the graph is going to hit a y value of 6 between these x value intervals endpoints. So again, we don't want to compare the 6 with the 5/2 and 4, right? We don't want to say, well, 6 is not between 5/2 and 4, so IVT doesn't apply. Well, we're not comparing the same things, right? We can't compare y values with x values. We're not, those aren't related. Or not, we want to compare y values with y values. So we got to do some additional work to actually find what those y values are and then compare those y values with this one and see if this value is an intermediate value, whether it's a middle value between our two endpoint y values. Okay, so that's our end goal. But before we do that, we have to establish our condition, right? So what's the condition that we have to put down first? Okay, what do we do with example 1? We first have to find what? Establish what?
Make sure they're continuous.
Okay. Continuous where?
An open interval.
Good, right. So continuous on the interval. And the reason why I want to specify that is because you may have graphs that may not be continuous, but it can still be okay for IVT as long as our interval is protected. As long as we don't have any breaks, asymptotes, holes between our interval, we can still move forward with the problem. And I want to stress that because sometimes you may come across problem in case, I mean, we're going to see it in this problem. You may come across some asymptotes and some holes. But if those asymptotes and holes are occurring outside the interval, then we're okay. We only want to protect the interval. We could care less what's happening outside the interval. We only need to establish a safe continuous region between our interval. Okay. Now this problem is not a polynomial, which means that we have to consider the fact that there may be a break in the graph and that break may affect our interval. We have to do some additional checks on our own. So the first thing we do is we need to find discontinuity. And we're trying to do it without looking at the graph, right? We don't have the graph in front of us. So we need to find the discontinuity and see does the discontinuity affect our interval? And the way that we find discontinuity is we look in the denominator. That is where we look, where if there is any breaks in the graph, it's going to tell us where it's located if we look in the denominator. So if I factor the numerator out, I'm going to get x times x plus 1 over x minus 1. And I want to just kind of remind us of a couple of things here. Okay, maybe we don't have to know this for this problem, but I just want to kind of remind us that the way you distinguish between the vertical asymptote and hole is you look to see, does the denominator cancel out with the numerator? If the denominator does not cancel out with the numerator, like this problem, because if I factor the numerator, I get x times x plus 1, then it must be a vertical asymptote. But let's say the problem looked like this. Let's say the factor that we found in the denominator does have a matching factor in the numerator, and we're able to cancel out. It is still a discontinuity, but it's a hole in the graph. Now, whether it's a hole or vertical asymptote, it's not going to affect how we do it because we're going to treat it the same way. But I'm just kind of connecting it. Some students were asking before, how do you know it's a vertical asymptote versus a hole? And I just want to kind of remind us of this property here. Right. But in either case, regardless, that is a discontinuity. But for this problem, our vertical asymptote is going to occur at 1, because if I set x minus 1 equal to 0, I get x equals 1. So there is a break in the graph. There's only one break in the graph because there's only one factor in the denominator, and that break is occurring at x equals 1. So this is a potential issue, right? Anytime we have a break in the graph, we have to pay attention. But for this problem, is that vertical asymptote, is that break in the graph going to affect our interval? Are we safe to move forward, or do we have to stop the problem? What do you guys see? So 1 is outside the interval, right? So we're safe, right? There's only one break in the graph, and that break is safely outside the interval. So we can continue moving forward. Our interval is safe. We can make our continuity statement. And we can move forward, okay? So I wanted to spend time going over this, because this is going to be the first step of pretty much every theorem that we look at. Every theorem, if there's a continuity condition, we have to always go through this, this process of looking for breaks in the graph, seeing if the break affects the interval, and then from there decide whether we move forward with the problem or whether we stop. If the vertical asymptote affects the interval, let's say the vertical asymptote was at 3.5, then the interval is now broken up, right? The interval is not safe anymore. It's not continuous. So if that's the case, then we say the function is not continuous on the closed interval. IVT doesn't apply. Okay. As soon as one of our conditions break down, that theorem breaks down. We can't go any further, and we just have to say it's inconclusive, or we can't move forward with the theorem because the conditions doesn't allow for that. Okay, so now that we've established our condition, there is a break. That break didn't affect our interval. We checked it. We're good. Now we can move forward. Okay, so now the next step is we want to know if this is a middle y value. Okay, but to determine if that's a middle y value, we first have to figure out what the endpoint y values are. Okay, so we're going to take turns plugging each x value into the function and finding the y values. And once we find the y values, we'll be able to compare it with this y value. 5/2, the same thing as 2.5. So I'll just take 2.5 and plug in. Use your calculator. And we get 35/6. And that approximates to be around 5.8. The other endpoint is f of 4, or is 4. We plug into the function. And we get 20/3, which is around 6.7. So now we ask ourselves, is 6 a middle value between 5.8 and 6.7? And the answer is yes, right? 6 falls between 5.8 and 7, which means that because we're starting at 5.8 and we're arriving at 6.7, the graph has to cross through a y value of 6 somewhere in between. Okay. Again, we're comparing y values with y values. We're looking for that. We want this to be a middle or intermediate value between our two endpoint y values. So for part A, we'll make our conclusion that this point is going to, that y value is going to be guaranteed somewhere between our two endpoints. So I'm just making a statement that 6 falls between my two endpoints. And I can safely conclude that there must be a y value of 6 on the interval from 5/2 to 4. Now part B is asking for the C value. Okay. We know that the graph is going to hit a y value of 6, but the problem is saying, can we find the actual location where the graph actually hits that y value of 6? So how can we find the x value if we know that we want the graph to have a y value of 6? Is there anything available to us that can help us solve for x? Can we use this function in any way to help us get there? What can we do?
Could we set it equal to 6 and then solve for x?
Good. Yeah. Remember, your function is just something to help find order pairs for us, right? If I know what the x value is, I can plug in to find the y, but it also works the other way around. If I know what the y value is, I can plug in and work backwards and solve for x. Right? This is how we can find any order pair that sits on the graph. Okay, so exactly, right. We have our y value, we're just going to plug in. So to find C, we're going to set our function equal to 6, and then we're going to solve for x. And C just represents the x value solution that we're looking for. Okay, so I'm going to set 6, plug 6 in the y location of my function. Maybe to make it visually easier to deal with, maybe I'll make that a 6/1. And if I make that 6/1, I can just think of it as cross product. Multiply this with this and set equal to this times this. This is going to be a factoring problem. I'll just go ahead and move everything over to the left side. 1x minus 6x is going to be negative 5x. Move the 6 over as well. Negative becomes a positive. So we ask ourselves, what multiplies to be 6 adds up to be negative 5? We got negative 3 and negative 2. Okay. We solve for C. or solve for x, sorry, solve for x, we get x equals 3 and x equals 2. And now we just represent that as our C values. So this tells us that there's actually 2 ordered pairs where the graph hits a y value of 6. So the graph hits the y value of 6 at order pair 2, 6, and also at 3, 6. So if we were to look at the graph, we're going to see the graph actually touches y value 6 in 2 locations. Now the next question is, do we keep both C values? Or how do we determine which C values to keep and which C value may not be what we want?
If we plug both of them into the equation and one of them comes out undefined?
Well, this is already defined, right? We've already established that these ordered pairs sits on the graph. So we don't have any discontinuity. The only discontinuity we have is at 1. So not quite. I mean, I'm glad you attempted, and it's a good thought, right? If that was the case, yes, definitely we would have an issue with C. But we've already found the one issue, and that issue is outside the interval. We've already established that we're dealing with continuous function, so we shouldn't be dealing. We're not going to run into any discontinuity issues. Okay, something else.
Does it have to be in between 5/2 and 4?
Yeah, good. So I want to keep reminding us about the interval. The interval is going to be important when we determine continuity. The interval is also important when we find the solution. Okay, this first step and this last step is going to keep repeating itself for a lot of theorems. Your theorems are going to look different in the middle, but the beginning and end is always the same. You're always looking to see if it's continuous. If it's not continuous, you got to decide whether you move forward or stop. And then when you find your C value, you got to compare that with the interval as well. The interval is what you're most concerned with. Anything that's outside the interval, we don't, that's not part of our problem. If there's a break outside the interval, we ignore it. If there's a C value outside the interval, we also ignore it. Okay. So whenever you see 2 solutions, that's a red flag. You got to go back and check, do both solutions fall inside the interval? Now, it's possible that both solutions fall inside the interval. If they both fall inside the interval, then we do keep both of them. But usually, 2 solutions indicates that there may be one that is not quite inside the interval. So we're looking at something between 2.5 and 4, but 2 is not between 2.5 and 4, only 3 is. So the only ordered pair where the graph is going to sit nicely between 2.5 and 4 is at this ordered pair of 3, 6. Okay, it's not a hard concept, but there's just a lot of numbers that we have to keep clear in our head, especially, getting confused between X values and Y values. And I want to just make sure that we're very clear, that we're comparing X values with X values, and then we're comparing Y values with Y values. Okay, you see how this X value 3 has to be between 2.5 and 4. And then we want the 6 to be between our Y values of 5.8 and 6.7. And it's easy to get mixed up between the numbers that we're comparing because we lose track of, are we dealing with X values or Y values, and and things get muddied when we're not clear what numbers we're dealing with, or whether we're dealing with, or if we confuse X values for Y values. Okay, this is as far as we can go before the bell rings. Sign up for AP registration if you haven't done so. I'll send out a reminder this afternoon. So I'll send out a reminder for this afternoon about tomorrow's iReady, but I want you guys to check in just for a minute or so that I can get attendance, and then you guys can do your iReady test. Okay, thanks everyone. Have a great day.
Thank you,
Thank
Mr.
you.
Yang.
Thank you.
Thank you, Mr.
Yeah,
Yang.
have a nice day.
Thank you guys.
Thank you.
Bye.
Thank you.
Thank you. Thank you.
Thank you.
Have a good day.